Hello everyone, this is the second problem from RMO 2016. This is based on some concepts from Fibonacci series. Uh, so it states that consider a sequence AK of natural numbers defined as A1 equal to A, A2 equal to B and AB greater than 1 and GCD of AB equal to 1 and AK plus 2 equal to AK plus 1 plus AK. Prove that for all natural numbers n, k, GCD of AN, plus k is less than AK plus AK divided by 2. So first we will prove one result, that is GCD of I will not write GCD, I will just write an comma n minus 1 to mean their GCD. So this is equal to 1 for all n. So we will prove this by induction. So by because a1 comma a2 equal to 1 by the problem condition. So the base case is clear. So let's assume that an comma an minus 1 GCD is equal to 1. So we will prove that GCD of an comma an plus 1 is also equal to 1. So GCD of an comma an plus 1 is equal. We can write an plus 1 as an plus an minus 1. And notice by Euclid's division lemma, we can write that this is also equal to an comma an minus 1. How did we do this? So this is a claim that GCD of a comma b is equal to GCD of a comma a minus b. So a very short proof, suppose this GCD is d. So d divides a, d divides b implies d divides a minus b. So because d divides a and d divides a minus b, so it should divide both of them. So it is one of the factors. So we will prove that this is the largest factor. Suppose d1 is greater than d, which is a GCD of a and a minus b. So which implies d1 divides a minus b, d1 divides a. So if we subtract them, which implies d1 divides minus b, which implies d1 divides b. So d1 divides both a and b. So d1 should divide GCD of a comma b. But GCD of a comma b is d, but d1 is greater than d. So this is not possible. So this proves that this result, and we are going to use many similar results like this. So this is a common structure for a proof of what we are doing. So applying this same lemma here, so GCD of an comma an plus an minus 1 equal to GCD of an comma an minus 1, but this is equal to 1 by the induction assumption. So we have proved it. So GCD of an comma an plus 1 is equal to 1. So hence by induction GCD of an comma an minus 1 equal to 1 for all n. This is the result. Second result is we will prove that an plus k is equal to an ak plus 1 plus an minus 1 ak. This is another result from Fibonacci series. We will again prove this by induction. So the base case I leave as an exercise. So for the induction step, what we do is, suppose this is true, we will prove that. So an plus k plus 1. So we need to prove that an plus k plus 1 equal to, like, add a 1 to k both sides. So that should be the result. So we will write an plus k plus 1 equal to an plus k plus an plus k minus 1. And by the induction assumption, an plus k is equal to an ak plus 1 plus an minus 1 ak. And an plus k minus 1 should be an ak plus an minus 1 ak minus 1. So this is equal to, like, take an common from first and third. plus 1 plus an minus 1 ak plus ak minus 1, and this is equal to an ak plus 2 plus an minus 1 ak plus 1. So we have proved for an plus k plus 1 this the same result. So the induction step is complete. So this result is proved. Now we will finally move on to the main problem. So GCD of an comma an plus k. We need to prove that this is less than ak by 2. So before that, I will prove another result. So by this result only, like this result that we just derived, this result, we get that a suppose ai does not divide aj for any I, because like ai does not divide aj, we can easily prove it using this. Suppose ai divides aj, so like j should be greater than I because it is an increasing sequence. So write j equal to I plus k. So by this statement we get that, well, let me write it down. So a j equal to, so this is a I plus k should be, so it should be equal to ai ak plus 1 plus ai minus 1 ak. So suppose ai divides aj is equal to ak plus I plus k. So using this we can get that ai divides the RHS, this one. So ai should divide ai minus 1 ak. So note that GCD of ai and ai minus 1 is equal to 1. So this implies that ai should divide ak. But see, k is less than j. K is less than j because I plus k equal to j. So k equal to j minus I is less than j. So if we take an induction, like first we will prove that ai does not divide ai plus 1, sort of. In the same way as induction, note that we have reduced it to a smaller case in this induction. So because we have reduced it to a smaller case, like we can do the same procedure, like write k equal to, if k is, if k, using this step, if k is less than I, then we have nothing to prove. If k is greater than I, write k equal to I plus k1, and we keep on doing this and we will prove this result. So we get, finally we can prove that ai does not divide aj for any ij. So using that, let's finally move on to the problem. So we need to prove that GCD of an plus k is less than ak by 2. So using this result, we get that this is, so this is equal to GCD of an comma an ak plus 1 plus an minus 1 ak. So by the same Euclid's division algorithm, we get that this is equal to, so we subtract this part off. You can prove that this result using the same steps I showed earlier, an minus 1 ak. We subtracted this part. So note that as we proved earlier, GCD of an comma an minus 1 not equal to 1. So this is equal to GCD of an comma ak. So this is equal to GCD of an comma ak. So this should be less than ak by 2 because see, suppose this GCD we denote by d. So suppose an comma ak equal to d, which implies d should divide ak, which implies that ak equal to some say alpha times d. So d equals to ak by alpha. So if we prove that alpha is greater than 2, we are done. So basically we need to show that alpha is greater than 2. So the only case left out is that because an does not divide ak as proved earlier, so alpha cannot be equal to 1. Alpha cannot be equal to 1. So alpha is greater than equal to 2. So suppose it is 2, then we need to show that an does not divide 2 twice of ak. So this also you can show by a similar procedure as mentioned earlier. I'm skipping a lot of details because otherwise it would be a very long video. So alpha equal to 2 also doesn't work. So alpha is not equal to 2. So if alpha is greater than equal to 3, so d equal to some a is less than a alpha by 2 and d is equal to GCD of an comma a n plus k. So we finally proved this. The result which I have not proved, I have proved a similar result. So you can use my other results to prove the ones I have not proved. So this was the solution. Thanks.